represents quotient. It's quotient. And the set of real numbers is denoted by R. We don't go into the details of what real numbers are, but I assume you somehow intuitively know what real numbers are. Okay, and the set of complex numbers is denoted by C. Of course, it stands for complex. And this is again a pair of two real numbers. But we have this I here. I is of course the square root, one of the square roots of -1. Okay, so that means I square is -1. So we have natural numbers, integers, rational numbers, real numbers, and complex numbers. And I think it should be obvious that this inclusion holds. Okay, natural numbers are a part of integers, which is a part of rational numbers, which are part of real numbers, which are part of complex numbers. Okay, and additionally, a real number that is not rational, it's said to be irrational. Okay, so real numbers minus rational numbers, this is the set of irrational numbers. Okay, so these are just conventions. Here are some more examples of mappings. Let's say we define a mapping F1 from natural numbers to a set of two numbers, -1 and +1, given by this. Okay, so this n comes to here, exponent. So if you put any natural number here, you get either +1 or -1. So when n is odd, this will be -1, -1. When this n is even, this will be an even +1. So in this case, this is the domain, and this is the codomain, and the range is the same as the codomain. And the next example, the mapping F2 from real numbers to real numbers. Let's define this function as this, x squared plus 1 for all real numbers. Okay, in this case, the domain is this R, and the codomain is this R, and the range is this subset of real numbers. Okay, all the real numbers greater than or equal to 1. Okay. And another mapping from natural numbers to rational numbers, defined by this. Okay, n divided by 2. And the domain is n, the codomain is q, and the range is this. Let's call it half integers. Okay, 1/2, 1, 3/2, 2, 5/2, and so on. So this is the set of natural numbers divided by 2. So this is the range. So far so good? Okay. Now, here are some important classifications of mappings. Let A and B be sets, and let F be a mapping from A to B. Okay, and the mapping F is said to be injective or one-to-one. Some people say 1-1. If whenever f of A1 is equal to f of A2 for any A1, A2 in A, then necessarily A1 is equal to A2. Okay? So what does it mean? Maybe I should write here. So we have A and B. So A1, A2, suppose they're different. Let's pretend they are different. But their destination in B are the same. So that means f of A1 is equal to f of A2. So if this is the case, this A1 and this A2 are actually equal. So if this happens, then this mapping is said to be injective or one-to-one. Okay? Next, the mapping F is said to be surjective or onto if for each B there exists A such that f of A is equal to B. Okay? In other words, F is surjective if the image of A is equal to B, equal to the codomain. Okay? What does it mean? From previous examples, you might have noticed that for some mappings, the image of A does not cover the entire B, right? In this case, if we pick this element, let's say this element in B, there is no corresponding element in A, right? Nothing comes to this point. So in this case, this function, this mapping is not surjective. So being surjective means the image of A covers entire B. So this covers entire B. So in that case, if you pick any element in B, there is always an element in A that corresponds to that point by this function. So that's surjective. Okay? And 3. The mapping F is said to be bijective or one-to-one and onto if F is both injective and surjective. So this should be easy, right? If the mapping satisfies this and this, then it's bijective. Okay? So here are some exercises. Any questions? No? Okay. Okay, let's move on to the next definition. So there are many definitions today. And let's say we have 3 sets, A, B, and C. And we have a mapping from A to B and another mapping from B to C. So we have this diagram. Maybe I should write like A, B, C. And this is F and this is G. Okay. So the codomain of F is B. But this B is the domain of G. Okay. Then we can combine this mapping F and this mapping G. And and define a new mapping called G circle F. Okay, so this is a new mapping which is defined by this rule. Okay, so the domain of let's call this G after F. Okay, G after F. So this is a new mapping from A to C. Okay, this is called circle composition, or just composition of two mappings. So for each element in A, we assign a value G of F of A, which is an element of C. Okay? So this means we first apply F of A. So pick one element in A. So this maps, this is mapped into F of A. And this is mapped into G of F of A. So after all, this element is mapped into this element in C. So this is the definition of this composition. Okay. So this rule is defined for each element of A. Then this defines a new mapping called G after F. Oh, G after F. And if there is no ambiguity, we simply write GF instead of G circle F. Okay, same thing. So this kind of defines a binary operation between two mappings. Okay. Now, here is one theorem. Let A, B, C be sets, and let F be a mapping from A to B, and G be a mapping from B to C. Then, if F and G are both surjective, then G after F is surjective. And if F and G are injective, then G after F is injective. And if both are bijective, then G after F is bijective. Sounds simple. Let's prove the first one. So in order to prove this theorem, we always have to go back to the definition. So in order to prove this, we should know what surjective means, right? So what was the surjective?